So, good afternoon, everyone. Today, our topic is effect of solvent on the rate of nucleophilic substitution reactions. So, what does it mean? Means how the solvent affects the mechanism, whether it will follow SN1 mechanism or SN2 mechanism. It depends upon the nature of the solvent. So, if we categorize polar solvent, further it is classified into two categories. One is protic, another one is aprotic. So let us understand the concept about protic and aprotic solvents. So first of all, we will study about polar protic solvents. Protic solvents, for example, methanol, CS3OH, ethanol, C2H5OH, water. These all are polar protic solvents. So polar means which have particular dipole moment. Particular dipole moment. So in all these molecules, these have particular dipole moment such as CH3OH. Dipole moment direction is always from positive to negative. Positive to negative. So it has particular dipole moment. So this is polar in nature, but as well it is protic in nature. How we can say it is protic in nature? The molecules which are capable of forming hydrogen bonds are known as protic solvents. So these all are the example of polar protic solvents. See, this is the one molecule of methanol and this is the another molecule of methanol. The oxygen of this molecule will interact with the hydrogen of another molecule through hydrogen bonding. So here, first of all, what is the hydrogen bonding? When there is interaction between hydrogen atom and one of most electronegative atom. So this bond formed between these two atoms will be known as hydrogen bond. One should be the most electronegative, another should be the hydrogen atom. So oxygen is the electronegative element, as it pulls the share pair of electron towards itself, so it will acquire partial negative charge. On this hydrogen there will be partial positive charge. So in another case, we can see also in the case of water also. In case of water, there is partial negative charge on this oxygen, partial negative charge, and here will be the partial positive charge, and here will be the partial positive charge. See, the oxygen of this molecule will interact with the hydrogen of another molecule, and the hydrogen of first molecule will interact with the oxygen of another molecule. Thus these molecules are forming hydrogen bonding. So these are polar protic solvents. This is the first peculiar property. The another one is polar protic solvent can solvate both cations and anions. What is the meaning of solvation? See, let us understand it with the help of example. We are supposing to dissolve NaCl in water. What happens when NaCl is dissolved in water? NaCl will dissociate into its ion Na positive and Cl negative. So what is next after dissolution also? That term is known as solvation. After dissolving, the another term we will use, that is solvation. Solvation means, see here, sodium has the positive charge. So this is cation. It is surrounded by the molecules of water. But which atom of water is surrounding towards itself? That is oxygen. So positive charge will be surrounded by the negative atoms. Negative charged atoms. Positive charge here is surrounded by the negative charged atoms. partial positive, partial positive, partial positive. So you can see there will be interaction between the O negative and Na positive, O negative and Na positive, O negative, Na positive, O negative, Na positive. So when a cation is surrounded by the opposite charge of solvent molecule, then this cation is stabilized. For this, we use the term solvation. Means the solvent here, what is solvent here? Water. Water is acting as solvent. So the molecule of water are stabilizing the sodium cation by surrounding around the sodium cation. So similarly, in case of chloride ion, it is also surrounded by water molecule. But here, in case of solvation, always opposite charges will interact to each other. Hydrogen has partial positive charge, oxygen has partial negative charge. Here, hydrogen have partial positive, partial negative, partial positive charges. So I am assigning the charges to show how these molecules will interact with chloride ion. So we know there are always opposite charges attract each other. So the H positive will stabilize this Cl negative. So H positive is from water. So the molecule of water are also stabilizing Cl negative, chloride anion. But which atom is interacting with chloride ion? Only hydrogen atom. So here what kind of bond is formed? Here hydrogen bond is formed. So, but in case of this, where central atom is Na positive sodium atom, in this case, sodium cation is stabilized by dipole interaction. So thus we have concluded that polar protic solvent can solvent both cations and anions. So this is the example how these charges are stabilized. Always these charges are stabilized by opposite charges. So our next is polar protic solvent. So these solvents are polar, means these all have particular dipole moment. So these are polar in nature. Aprotic means these do not form hydrogen bonds. So these are some examples: DMSO, dimethyl sulfoxide, DMF, dimethyl formamide, ACN, acetonitrile, THF, tetrahydrofuran, DCM, dichloromethane, and acetone. So these are the examples of polar aprotic solvent. One of them is DMSO, dimethyl sulfoxide. So consider the same example. We have been dissolving NaCl in DMSO. What happens? Na dissociated into its sign, Na plus Cl negative ion. So in case of DMSO, this oxygen is heading towards Na positive. There is partial negative charge on oxygen and there is partial positive charge on this sulfur because of the difference in the electronegativities of both these two atoms. Partial negative, partial positive, partial positive, partial negative charges. So then the oxygen atom of DMSO will be interacted towards sodium atom. Here also oxygen atom is also interacting with sodium positive. So in this case, DMSO also stabilizes sodium cation by dipole interactions. See here, chloride ion. There is no hydrogen atom in solvent. DMSO have no protic hydrogen. So here there is no formation of hydrogen bond. Thus, polar aprotic solvent stabilizes only cations. Cl stays naked as well. So Cl negative here is not stabilized. So this is the peculiar property of polar aprotic solvent. So moving to the topic, how these solvent affect the rate of reaction. So it is concluded that the polar protic solvent favors SN1 mechanism and polar aprotic solvent favors SN2 mechanism. But why? The question arises here. Why this happens? So just we have understand the basic mechanism how polar protic and polar aprotic solvents are stabilizing cation and anions. So just remember the difference between polar protic and solvent and polar aprotic solvent, which will help us to understand why both of these favoring as differently SN1 and SN2 mechanism. See here I am taking here the case of SN1 mechanism. In this case I have chosen the substrate tertiary butyl bromide. Here you can take X is equal to Br. So X is Br. And OH negative, it is a nucleophile. And what is the source of nucleophile? You can consider NaOH, either QH. Out of these, both of can act as nucleophile. Both are the sources of OH negative. So OH negative is coming from NaOH. So what is happening, as we have discussed in a previous lecture, OH negative is nucleophile. It will attack on this substrate. But how? First of all, this leaving group will be expelled from here. Thus, there will be formation of carbocation. Carbocation here is formed. CH3, CH3. Here will also come CH3. So you can see this trigonal planar structure of the carbocation plus Br negative. This is its counter ion. Then in second step, nucleophile will attack over this carbocation and thus it form the final product alcohol. Okay. So in this reaction, what is the rate determining step? The step in which there is formation of carbocation. It is the slowest step. As in SN1 mechanism, there are two steps. First one is there is formation of intermediate and the second one is the attack of nucleophile. So rate of reaction depends upon the step in which there is formation of carbocation. So rate of reaction is depends upon the substrate, that is CH3, 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 X. So the rate of reaction is depending upon the substrate tertiary butyl bromide. Let see, this is the energy profile diagram, how this reactant is converted into the product. Here is the energy of reactant. What happens when carbocation is formed? So when carbocation is formed, this bromine group is expelled from here, and here is the energy of this carbocation. This is the energy of carbocation, and this is the energy of the product formed. Suppose this reaction is carried out in the DMSO. DMSO is polar aprotic solvent. So what will DMSO do here? What is the role of DMSO? DMSO, this oxygen has partial negative charge, sulfur has partial positive charge. The oxygen atom from DMSO will stabilize this carbocation, so it lowers the energy of intermediate. Clear? So this Br negative counter ion, this is not stabilized here in case of DMSO. If we consider another case in which we use polar solvents such as water, then what happens in that case? Here I am taking the example of water. Please just draw the structure of water here. OH, H, H, OH. Partial negative charge, positive charges. Just assign the charges over this molecule. The oxygen atom of water will interact with carbocation and stabilizes the carbocation. On other hand, the hydrogen atom will also stabilizes this counter ion, bromine negative ion. So in case of polar solvent, both the species, carbocation as well as counter ion, are stabilized. But in case of DMSO, only carbocation is stabilized. So this is the energy profile diagram in case of DMSO. But when I am using polar solvent, what happens? The energy of this intermediate decreases. It lowers the energy of intermediate to this extent. As we have been taking the reactant, same reactant in both cases, so the energy of the reactant remains same and the product form is also same, so the energy of product is also same. This reactant is neutral, so water do not stabilizes this reactant, DMSO also do not stabilizes the reactant, these only stabilizes the intermediate. So as we know, the rate of reaction depends upon the substrate. It does not depend upon the nucleophile. So it do not affect the energy profile of the nucleophile. So here we are taking only the tertiary butyl bromide. So this is a energy profile diagram. So here there is lowering in activation energy. Activation energy. Thus, from this we summarized that SN1 is favored by protic solvent, polar protic solvents. Let us consider the case of SN2 reaction. What happens in case of SN2 mechanism? Here we have taken the substrate methyl bromide and OH negative is the nucleophile. In this case, transition state is formed. As you can see here, the bond between carbon and bromine is a dotted line. It means this bond is getting weak. And here the bond between OH and C is this is also dotted line. It means this bond is forming. So this bond is forming and this bond is breaking. This dotted line represented. Here is the H. So I have represented this transition state with the double dagger and finally the product is formed. This is a one-step mechanism. As in previous case, there are two steps in SN1 mechanism, but in case of SN2, there is only one step. So if we study the energy profile of this reaction, you can see here is the methyl bromide and OH negative. In case of SN2, the rate of reaction depends upon both reactants, both substrate and as well upon nucleophile. So we are taking the energy of both reactants over here. So this is the energy of transition state and this is the energy of product. Here, same if this reaction is performed in DMSO, if we are conducting this reaction in case of DMSO, what happens? O CH3, partial positive charge, partial negative charge. Okay. Nucleophile has more electron density as compared to this transition state. As here are partial negative charge, here is also partial negative charge over there. So nucleophile has more electron density as compared to this transition state. So in case of DMSO, this is energy profile of these reactions when methyl bromide is converted into the methanol. Okay, so like but what is happening in case of polar solvent? If here I am using water as polar solvent, partial negative charge, partial positive charge, partial positive charge. Here is the partial negative charge. This partial negative charge will stabilized by the H positive of these atoms. And in case of DMSO, this is also stabilized by the partial positive charge of the sulfur. So this is same for both cases, stabilization of this transition state. But what is the role of water molecule here? Water molecule also stabilizes this nucleophile OH negative. These also stabilize the OH negative molecule. So if water molecule stabilizes the OH negative molecule, it lowers the energy of the substrate. So energy of the substrate is gets lowered. See how? Here is the energy of substrate, it gets lowered. And if I am drawing the energy profile in case of polar molecule, so you can see the energy of nucleophile is lower to larger extent as compared to transition state, because transition state is less dense. I have already said to you the negative charge on this transition state is less as compared to nucleophile, so this is less stabilized as compared to the nucleophile. So what is happening? Previously the energy of reactant was this and the transition state was this. So this was the activation energy. But now what happened, as the energy of reactant is more lowered, so the difference between transition state and reactant is increased. So it's difficult to cross this energy level. Thus, in case of polar solvent, due to stabilization of nucleophile, it do not favors the reaction. So SN2 is favored by only non, sorry, polar protic solvent. So this was the today's lecture about polar protic and aprotic solvents.